webcam. Okay, so for some reason it's not recognizing my, hold on. You know, using this once a week, you always kind of forget what the settings are. Let's see. Those of you wondering what I'm doing, I'm trying to, oh, you know what I think I know what, select settings. For some reason, it's not recognizing the webcam on my larger screen. I guess there's no separate preference for the webcam. I'm going to exit out and come back in. I'll be right back. So let's see if that helped. No, it hasn't. So if it is okay with you, I will do the webcam from my laptop, which then is awkward because I'm looking somewhere else when I'm talking, and it just seems a little weird looking at me from the side view. It's not my best side either. So let's try that, and then maybe in the break I will try to fix it or something. So if I look weird because I'm not looking at you, please understand. And let's get started. So we're going to talk about denture acrylics and then composites. You actually don't play with denture acrylics until much later. However, I think you may have started or will very soon start playing with composites. So because of that, we're going to do composites, but denture acrylics really is the precursor to composites. It's a much simpler system and a very similar system. And so that's why we are doing both of those together. Okay? So as far as denture acrylics is concerned, acrylic polymers have been biomaterials for a really, really long time. And they discovered it as a biomaterial during World War II, when they had these fighter pilots on these B-52 bombers. And the planes that get shot and, glass kind of shattered all over and then got embedded in people. That glass was actually made with polymethyl methacrylate, an acrylic resin, the same one that's used for denture acrylics. And so they were able to bring them back, and when they observed them, they were very surprised to see that there was really very little or no inflammatory reaction against this material. And so since then, they've been using it in medicine and dentistry and many different areas. So they use it as orthopedic bone cement. Really, without much sophistication, it's pretty much the same material they've been using for the last 50, 60 years. The bone cement industry is almost like a cartel. Very few companies exist selling bone cement. This material is actually very cheap, but of course, if it's a bone cement, it must be like 100 times more expensive. And they are kind of resistant to making a lot of changes because they've cornered the market. They don't want to cannibalize their own products. We've actually developed an antimicrobial bone cement with silver nanoparticles years back, and despite the fact that there are, while not a large group of patients who suffer from infection because of bone cements, there's still quite enough patients where that would be helpful, and they weren't very interested. It's kind of one of those things where if it's good enough, why bother paying for patent or anything else and have that developed? So anyway, bone cement in the medical industry. In fact, even the hard contact lenses, some of them are made out of polymethyl methacrylate. I know that most of people use soft contact lenses instead, but anyway, the hard ones were made with PMMA. And of course, in dentistry, it's used in denture bases and teeth, repair materials, crowns and bridges, and impression taking, temporary direct film resins, and so forth. Okay? So let's start off with the definition of acrylic resins. And these are basically polymeric materials derived from acrylic acid or methacrylic acid. The difference between these two is just that there is a methyl group on one side. Okay? And the most important material in dentistry is methyl methacrylate. As you can see the chemical formula here. It's a very, very small molecule. Okay? Now, acrylic resins, as we learned last time, is cured through addition polymerization. Okay? And they're available as heat-cured systems, cold-cured systems, and even light-cured systems. And it refers to the method of polymerization. And I don't know if you remember that detail in the addition polymerization part of the polymers lecture, but for heat-cured systems, which is the most widely used acrylic material for denture acrylics, an accelerator is not needed because the accelerator itself is actually the heat. Okay? And once you pass about 60 degrees, benzoyl peroxide will actually start to form its own free radical, okay? And activate or initiate the addition polymerization, and then you get the polymerization happening. The reason this is so widely used is because they heat-cured materials tend to have the highest molecular weight and consequently the lowest residual monomer, and that leads to the highest strength. However, it does require a special heating protocol. Now, cold cure resins or self-cured or chemically cured resins do exist, and they're really a lot more for repair materials. But in this situation, an accelerator is or an activator is needed to get the benzoyl peroxide to form a free radical, okay? Because there's not enough heat there. The reason why this is not as widely used is because they tend to have lower molecular weight, just not enough energy to drive the polymerization. They have a higher residual monomer because of that, about 10 times higher residual monomer. They also have higher porosity, mainly because of the mixing, and they do have lower strength. Now, the denture acrylic actually, even the heat-cured denture acrylic, actually is not completely a heat-cured system. In other words, we'll see later that you mix the powder and liquid, and it actually starts to polymerize. So it is kind of self-cured, but the amount of accelerator and initiator is different. And so here you do need to heat cure the material to get it all the way, to cure all the way. While here you don't need it at all. Okay? So many of the heat cured systems are actually self-cure partially. Okay. So in the cold cure system, I mentioned that you need an accelerator, and it's to make the initiator unstable, and they're usually aromatic amines. And because of that, you need to have two separate parts. That's why you have the liquid and the powder. You're separating the initiator, benzoyl peroxide, from the activator, okay? And so that it doesn't cure by itself. Okay? And so you need a two-part system. And the most popular one is dimethyl paratoluidine, or DMPT. Now, for these two lectures especially, we will talk about a lot of chemical names, and you will be responsible for those. Your handout has bolded chemical names. Those are the ones that you need to memorize. You need to at least know the acronyms. And the reason is because these are so common, so foundational, that if you're going to talk knowledgeably about composites or acrylics or whatever it might be, you really do need to know that. And any article you read on dental materials will contain these chemicals. So you need to know that. Okay. Let's see. Okay. So as far as the reaction is concerned, okay, and we've seen something similar, I think, in just bullet form before. You have DMPT here with a lone pair of electrons on the amine. Okay, and that lone pair of electrons is what attacks the oxygen-oxygen bond here for the benzoyl peroxide. Okay? And then it forms a complex with one, and you get a benzoate ion being given off. And then that dissociates, and you end up with the benzoyl peroxide radical. Okay? So this is what then enters into the polymerization as the initiator system. For light cure systems, okay, they're not as widely used, but they are becoming more popular. It's mainly because of the way dentures are processed and the armamentarium they already have. So that's why they're not as popular. And they require a light-sensitive initiator system to get this to go. So it needs to be some kind of activator there, right? Light activator. So in this situation, you have camphorquinone, which is a photosensitizer, which is the activator for the amine. Okay? So in the cold cure system, the amine is the activator, the aromatic amine. But in the light cure system, the aliphatic amine, which doesn't have a benzene ring in it, is the initiator. So the camphorquinone sensitizes the amine to light and gives it energy to form a free radical. Now, however, camphorquinone also forms a free radical in that reaction. So sometimes you will hear people say camphorquinone is a photo initiator, and they are not wrong. Okay, so it actually has both dual roles. So it could be referred to as a photosensitizer, an activator, or a photo initiator. Okay? Oh, by the way, please do not hesitate to turn on your mic and interrupt me if you have any questions. Sometimes that's just quicker than typing the question in the chat. So, okay, so as I mentioned, the denture acrylics come in two parts, a powder and a liquid part. Okay, and the powder basically mostly consists of acrylic polymer beads. These are polymethyl methacrylate polymer beads. So the manufacturer has already cured methyl methacrylate and then ground it down into powder and then giving it to you this way. And mainly it's to reduce shrinkage and the heat generated, which we will talk about, and the heat is generated in the reaction. It also contains the initiator, benzoyl peroxide, and you kind of want to keep the initiator away from the monomer, which is in the liquid side, because you don't want it to spontaneously react. If it's in the monomer and it's left on the shelf for a long time, it could just react just by statistical reaction, with the statistics happening. And there's always going to be some benzoyl peroxide that becomes a free radical. Anyway, so you want to keep that with the polymer beads. And then it also contains pigments, as shown here, mainly because polymethyl methacrylate is clear. And to make denture, you want to make it look really lifelike. So you have these pigments to make it pink or white for denture teeth, and so forth. It also contains a plasticizer, which softens the polymer, decreases dough forming time, which we will talk about, and increases working time. Okay. So this is really more for making the mixture more usable and to have it cure in a practical time. The liquid contains mainly the monomer, okay? And then it also contains an inhibitor, because, as I said, with the monomer can actually also spontaneously react and form a free radical. So sometimes it's because of heat. Sometimes, so whatever it is, so you have an inhibitor to react with stray free radicals so that it doesn't polymerize, and then it extends the storage life and also the working time. It has the accelerator here, separated from the initiator, okay? And it also contains a cross-linking agent, which is an acrylic monomer with two double bonds. It's a diacrylate or a dimethacrylate, okay? And basically you have two sets of reactions going on, one on each side, and it bonds the neighboring growing chains together, okay? So this is just light micrographs of these PMMA beads. And you can see just pigments that are locked inside. So they added the pigments to the monomer, cured it, and then ground it down. Or they just put pigments on top, just mix it in, and have it just kind of absorbed onto the surface of the beads. This is hydroquinone, an example of an inhibitor. You can see the hydroxyl groups, which can react with the free radicals to prevent the reaction from happening. Obviously, you'll have only very little in there. It's just to prevent any stray reaction happening. And when the reaction is initiated, initially there's a slight delay because all of these inhibitors need to be used up before the reaction actually can happen. Okay. This is a cross-linking agent, which is in this case glycol dimethacrylate. And you have two, as you can see, carbon-carbon double bonds that can enter into the polymerization reaction. And you'll have one chain growing this way, another chain growing that way. And this polymer here, or this molecule here, acts as a bridge between the two. So you have here methyl methacrylate, okay, growing in a chain, okay, in the presence of glycol dimethacrylate, okay? And you can see here that you have two chains growing, okay? This is the methyl methacrylate going into polymethyl methacrylate with glycol dimethacrylate incorporated, and another one growing here. And the glycol dimethacrylate is bridging the two chains together. So in processing denture acrylics, one of the most important things that needs to be controlled is the powder liquid ratio. So powder monomer or polymer monomer ratio. It should be either 2.5 to 1 weight to weight, or 3 to 3.5 to 1 volume to volume, depending on the manufacturer. Okay? one thing that I want you to be careful of when we talk about whether it's the ratio or weight percents or volume percents is that a lot of times some manufacturers will talk about weight percents or weight to weight ratio. Another one will talk about volume to volume or volume percent. Sometimes they tell you both. Most of the time they only tell you one of the two. And you need to be mindful about which one they're talking about so that in this situation, when you mix, you don't mix the wrong ratios. But also when you compare product to product, especially down the line when we talk about composites, and you're looking at their properties, sometimes they will talk about filler weight percent or filler volume percent, and they will tend to talk about weight percent because that's a higher number. And a more honest company would talk about both or the volume percent because that's really more comparable. And so you need to kind of be careful about what manufacturers are talking about. And so just just be a little bit careful with weight to weight and volume to volume, or weight percent and volume percent. Okay. Anyway, if the ratio is too high, in other words, you have more polymer than you should, or not enough monomer than you should have, then you'll get insufficient wetting because there's not enough liquid to wet all of the powder properly. And that creates porosity because you're going to have voids in between the particles and, as the liquid wets the particles. You also will get insufficient plasticity because since there isn't enough monomer, the reaction progresses really quickly and you get to a solid state really quickly, and it doesn't give you enough plasticity, doesn't give you enough working time. And you also get incomplete polymerization because you just didn't have enough monomer to polymerize the whole mass. Okay, so while all the monomer gets used up and polymerized, that entire mass does not have enough polymer. Okay? Now, if the ratio is too low, okay, not enough powder or too much liquid, okay, then you get excessive shrinkage because the shrinkage, which we will talk more about later, mainly comes from the monomer turning into polymer. Okay? And because of that, you get poor dimensional accuracy. I think I mentioned this to you last time, but it's very important to understand or keep in mind the differences between accuracy and stability. So accuracy, again, is what you get after you finish processing. Stability is over a long period of time after you've made it. Okay? So in this situation, as soon as you make the denture, it won't fit because of the excessive shrinkage. Okay? So in the stages and the physical reaction of this, and we showed you videos of this last time, and I'll show it to you again. Basically, there are several stages. You start off with the sandy stage. So that's when you first mix, okay? And the monomer begins to wet the powder, and you just kind of get a granular mix, like just wet sand, okay? And just to refresh your memory, this is what we saw last time. So Corey here is mixing the powder of lucitone and the liquid. So basically about a 3-to-1 volume to volume ratio. And you can see that as she does mix that, it looks really sandy. Okay, basically it's just wet sand that you'd see at the beach. Okay. The next stage then, okay, is the stringy stage. So as the monomer begins to react, get absorbed by the polymer beads, you start getting more of a single mass, but at this stage it's still sticky because the molecular weight is still low, and this is what you can call the too soon to use stage. Okay, so if it strings out like that, the reaction hasn't gone along enough to flask it and then to cure and then to put it into the water. Okay, and again, this is the video of that. So you see that it's basically a mass, but you can see how it strings out and it's kind of sticky, right? The next stage is the dough stage, okay? And this is the just right stage. This is when you want to actually pack your flask. Now, one thing I want you to notice here is something called doughing time, okay? Doughing time is the time it takes from the initial mix all the way to when it gets to the dough stage. And that's important because the manufacturers have to control how long it's going to take. You don't want it to take too long, right? Because otherwise, then you'd be just waiting. But you don't want it to be too short as well. So they will report on their instructions what their doughing time is, so they should. Another name for this, because it's a little bit confusing, is dough forming time, which I prefer because it tells you how long it's going to take to form the dough. Okay, time to get to the dough stage. Okay, so anyway, so you get to this dough, and that's when the mass separates cleanly and looks like this. You can see that it's not as sticky. Okay, it's a little stringy, but still you can see it really does look like a dough, play dough type of a material. Okay, and as it polymerizes a little bit more, it'll break apart more cleanly. But you can see it doesn't stick to the hands. Well, that's what it looks like. And you can roll it up, yeah, just like that. Great. The step after that, then, is the rubbery stage. And this is the stage where it's already too late to flask because now it has some mechanical strength where when you put it inside the flask, it doesn't spread to all of the detail and reproduce the fine detail of the cast. Okay, so this is the gone too far stage, right? Now, one thing I want you to also notice here is, I forgot to mention that there's something called the manipulation period. And that's the time that the material will stay in the dough stage, okay? Where you can actually manipulate it, put it into the flask, and put pressure on it, have it really reproduce the detail, okay? So keep that in mind. And it's also called the working time, okay? Manipulation period. Anyway, so this is the rubbery stage. And that's kind of already too late to flask, and you definitely don't want to flask in this stage because, as I said, it won't reproduce the detail. You can see that that's what it looks like. Yeah, you can see that she's pressing it down, and it really won't spread easily. Okay, so the flask will have trouble closing and making contact with each other as well. And you're probably wondering, I keep talking about flask. Well, we will see that a little bit later. Okay? Yeah, you can see how rubbery that is, right? It's really like a very thick rubber band. And then the final stage is the solid stage. And obviously, you're not going to flask anything with that, right? And I think we showed you this. I showed you this last time. And basically, at this stage, the material is like a rock. Okay? It's like a golf ball, very, very hard and strong. Okay. So I mentioned dough forming time or doughing time and working time or manipulation period. Okay, so don't get those terms mixed up. Okay, but there are multiple terms for these. But there are standards for how long it should be for denture acrylics, and so basically the standard is that the dough forming time should be less than 40 minutes, but commercial brands are actually less than 10, and you really don't need it to be that long, right? The working time should be greater than 5 minutes, okay? And that's what and different manufacturers will have different working times. So it's kind of important to know how quickly you like to work and pick the right brand for that. Okay. Now, there are things that affect dough forming and working times. Okay, first one is particle size. So if you reduce the size, okay, you reduce the dough forming time. And the reason is because of the increased surface area that you get. And so the liquid, when it wets the surfaces of the particles, it will be able to wet more of the surface of the mass. And so because of that, the reaction happens more quickly and it reduces dough forming time. Now, once it gets to a dough, now you would think that, okay, well, why does it not affect working time? Okay. As you see, I didn't put anything there. Okay, why do you think that's the case? Anybody? This is a tough one. One extra credit for somebody who guesses right. Am I the only person here? No wild guesses. Doesn't hurt to try. Okay. Don't be shy. You can just turn on your mic and say it. Bailey says, does it depend on the amount of water you use and the plasticizing effect? No. Answer choice B, yes. Okay. So a couple other people type in. Can you repeat the question? So, does it depend on the manufacturer? No. So the question is, particle size affects dough forming time to get to the dough stage, because the smaller the particle, the higher the surface area to volume ratio. So there's more area that the monomer can wet in the same amount of same mass of powder. Okay, so more reactions can take place at once. So the dough forming time is reduced. It gets to the dough stage much more quickly. But if you notice here, there is no effect on working time, or at least I did not put down working time here. And the question is, why does it not affect working time? Or does it? Inhibitor readily relaxes small particle size. Actually, the inhibitor only reacts with the monomer, so it's not dependent on the particles. Smaller polymers in powder, and for this, they can take up the monomer more rapidly, decrease. Yes, so it decreases dough forming time, yes. But why does it not affect the working time? Because they are long polymer chain now, and then it depends on ratio of polymer. Okay, so Michael has a very, very good answer. Jimin says working time depends on strength of bond formation, willingness rather than surface area. Not quite. So I'm going to give the correct answer to Michael because it's close enough. So when you get to the dough stage, okay, let's say I have product A and product B. Product A has much smaller particle size. Product B has larger particle size. Okay? Same amounts that I use. And then I mix them. Product A obviously naturally gets to the dough stage early, and then B gets to the dough stage later. Now, when both of them enter the dough stage, which one has a higher molecular weight? Which one has a higher molecular weight? Bigger particle size, larger particle size, bigger particle. Oh, wow. They are the same. Thank you, Taylor. They are the same. Why? Remember, mechanical properties, which the dough, the physical dough structure or feel is, the mechanical properties are dictated by molecular weight. So since they're the identical chemical formulas, when they get to the dough stage, they are identical molecular weight. So once you get to the dose stage, there's no effect on the working time because they are at the same molecular weight. Now, product B got to the dose stage later, but when they are at the dose stage, the polymers are the same size. Okay. So Michael, congratulations. You get 1 extra point for your quiz today. Okay. Hold on, let me just make a note of this so that I don't forget. All right. Wonderful. So what does working time mean? So basically, I told you when we go back to the previous slides, okay, working time is the manipulation period. So once it gets to the dose stage, okay, working time is the manipulation period. Okay, both terms are used, and this is a time where you can mold the flask with this dough. Okay, it's the time period where it remains in the dough stage. Okay, so that's what the working time is. That's when you can actually work it into the denture shape. Okay, all right. So that's important. Okay, so there is a madness to when I say that it affects dough forming time and working time, and when I only talk about dough forming time. Okay, so it's important to understand the concept. So should there be a question like this, okay, about things that affect dough forming and working times? Yes, I guess you need to memorize it just for swiftness, but you really do need to understand what's going on at the molecular level so that if you get stuck, you can actually work through this, okay? And that will help you because when you understand the system, you don't have to memorize this. Okay? And I don't like to give exams or quizzes that don't have enough time because I don't think that tests anything. And so it's really more important for you to understand what's going on. Okay. Anyway, because there's so many things to memorize, unless you have a photographic memory, impossible. Okay. So the next thing that affects dough forming time and working times is, and I use these terms because I feel like they are more indicative of what you're doing. So I prefer these terms, but again, if I say doughing time or manipulation period, you need to understand what I'm talking about. So powder molecular weight. So if you have a powder with higher molecular weight, okay, it increases dough forming and working times. And the reason is because the higher the molecular weight, and you have to think of this as having the same particle size. Okay, so if you have a higher molecular weight, it becomes more impervious. So it's more difficult for the monomers to penetrate into the powder, the particle. And so it's difficult for the reaction to happen as quickly. So it takes a little bit more time for the monomer to penetrate and then react. And so that's why it increases dough forming time, okay? And it also increases working time because the reaction is having a little bit more difficulty happening with the powder, okay? If you have a plasticizer, which most do, but depending on how much plasticizer but the reason plasticizers are added is because it reduces dough forming time but increases working time. Now, these two are related, okay? What the plasticizer does is it softens the polymer. A plasticizer is kind of like a solvent, just kind of gets in between. It's a very small molecule and kind of gets it in between, softens it up, swells it up a little bit. And so because of that, the monomers are able to penetrate better, okay? So it actually allows the reactions to happen quicker. But I hope you're asking the question, well, if that's the case, why is working time increasing? Okay? Well, it's because the plasticizer keeps the material soft. Okay? So even though at the same molecular weight, it's softer, so it's still manipulable. You can still manipulate it. So because of that, the working time is increased. So it needs to get to a higher molecular weight to get to a rubbery consistency. I hope that was clear. Okay? So these are kind of opposite phenomena, but the effect is not directly opposite. Okay? So this is a little tricky. Temperature. Okay? So if you reduce the temperature, if you're working in a cold room for a self-cure system, then you're going to increase working time. I mean, it's just basic, just energy to drive the reaction. Since this reaction can be driven by heat, obviously, as I mentioned, heat cure resins just have a lower amount of, initiator and other chemicals to drive the reaction. You can see that, since heat can affect the reaction, it actually does speed it up. Okay? But this is really more of an artifact because it just depends on the temperature of your clinic or your lab. Polymer monomer ratio, here we talked about this. If there is too much powder or too little liquid, it decreases dough forming time because all of the monomer gets reacted quickly. Okay? Again, there's no effect on working time because of the same reason. Once you get to a certain molecular weight, okay, then the reaction proceeds the same. Okay? Self-curing, if you use a cold cure material versus heat cure, you actually reduce the working time because, as I said, the heat cure basically does not cure fully because it doesn't have enough initiators. It cures kind of slowly because you don't care how quickly it cures. Basically, you want it to get to the working, the dough stage, you manipulate it, and then you flask and you put it in heat. That's when you want it to cure quickly. So that's why self-cure resins, self-cure denture material have a shorter working time. Okay. So another factor is the use of mold lining. Okay. Basically, it's to line the plaster, the stone, okay, stone cavity where it has the negative impression of the denture that you want to make. Okay. And basically what it does, the reason you use it is because you don't want the monomer to penetrate into the stone. The stone is porous. So if you don't have this on there, then what happens is that you get a very rough surface because of the porosity of the stone. And also kind of sticks to the stone too. So you don't want that happening. And on the opposite side, because the gypsum or the stone has water in it, you don't want the water kind of imbibing, absorbing into and diffusing into the denture acrylic because then it'll cause blanching. Okay? And generally they are calcium alginates and silicone emulsions. I believe this is a brand that you use or we use here. Okay? Initially they used tin foil. And so you had to painstakingly get a really thin piece of tin foil and then kind of like push it into the negative impression. And it was very tedious, but now this is what we use. And it's an alginate solution. And when you kind of brush it onto the surface, it forms calcium alginate. Okay? And you get a little thin coat there. And I think they even spray sell them as sprays. So after that, we get to the packing stage. Okay. So, and as I mentioned, the doughy stage, oops. Okay, the doughy stage is when you want to pack it into the flats. So this is a negative impression. And because if you pack it in the sticky stage, which I told you was too soon, you get excess trapping of air. You don't have enough mass or mechanical property of that material to be able to push back against the flask, okay, and cause that pressure. You need that pressure because you mix it and you're going to get porosity. So when you flask it, you have to put the pressure on it to get rid of the bubbles. Okay, so but you don't get enough pressure in the flask because it's too weak. Okay, and it's also not viscous enough, and it could flow out from the sides, and then now you're going to have gaps in between the stone and the denture. Okay? So you get poor dimensional accuracy there. Now, if you pack it in the rubbery stage, okay, it's too viscous, it's too rubbery, okay, and it won't fill all of the detail in the cavity. Okay? And it also prevents the two halves of the flask making contact, metal to metal contact. So you just won't get, again, an accurate denture made. And these are packed and then molded using one of three, or actually there are more than three, but they're generally one of three different types of techniques. Compression molding, which is the most widely used, injection molding, which is gaining popularity, and you also have fluid resin technique as well. Now, I have a really good video of the injection molding technique, and it helps us see what the process looks like. I have also put a video on Canvas on the compression molding. It's just that it's so detailed and a little long for this lecture. So instead of showing you, I've left it there for your reference if you want to better understand this and get that kind of a better grasp of what's going on with the heat curing and the compression molding. So you can watch that in your own time. Hopefully this video works. So the separator is the mold lining. So in this case, it actually does use a heat cure acrylic that does not form a dough stage. They just inject it. In this case, this material does not have any initiator in it. I'm sorry, accelerator in it. So the compression molding video, I strongly urge you to, at some point, when you have time, I don't know when that's going to be, but at least take a look at that. So in the third year, this year, I heard that a lot of the students were kind of clueless about this process for some reason. And I think it's because I'm showing you this so early. I mean, this is your first semester, that students, a lot of you may not remember this when you get to the third year. And it's not just this, but it's also later on when we talk about casting investments in metals, the lost wax technique. Some of these videos are not just for illustrative purposes, but also because we don't have this in the curriculum anymore. So the casting investments, I used to teach that, and we've taken that out because a lot of that work is done by the labs. But because we've done that, and you don't actually do that in the lab, sometimes it makes it difficult for dentists to be able to communicate with the labs. And so it's important that you have at least a certain level of knowledge. So, don't just kind of brush off these videos. Definitely try to pay attention when I show them to you. Okay, it's at 8:53. So let's take a 10-minute break, and we will start up again at 9:03. And I'm not going anywhere. If you have any questions, feel free to ask. And we'll see you back in 10 minutes. Hey, sorry about that. Can you hear me now? Oh gosh. So obviously you did not hear my last 5 minutes of rambling. So let me go back. So the first question was from Corey, and she was asking, she was asking people uh, why this heat curing lucitone was not a self cure, and how they explained it getting to the doughy stage. Some people said the monomer was evaporating. Other people said the monomer was polymerizing. The correct answer is yes, the monomer is polymerizing. In the situation where you have a heat cure system that they sell that is two-part system, powder liquid, you'll know for sure that it's actually a self-cure. The difference is that the initiator and accelerator levels are much lower, and because of that, it doesn't cure to completion as well as a self-cure system. What is the important factor in this is controlling the working and the doughing times so that the dentist can manipulate the dough properly, flask it, and then the cure, the rest of the cure is completed by the heat. And the use of heat, I'm getting a lot of messages. No, lucitone is not strictly heat cure. They don't understand the system. So the heat, the reason why they heat cure it is because you can drive the reaction to a much higher molecular weight and get better mechanical properties out of it. Okay, and the beauty of the compression molding system is that you have to mix the powder and liquid, and as you compress it, you get rid of the air bubbles, which gives it further better mechanical properties. Okay, now there are real heat cure systems. The video I just showed you on the injection molding is a true heat cure system. It's basically, it doesn't react by itself, and it only reacts with heat. And that's because they don't have to get it to a doughy stage. Okay, so great question. So keep that in mind when, I don't know, when you talk to the lab or other people and they tell you that this is just purely heat cure, you know that it's called a heat cure, but it actually is a self-cure that's designed not to cure that well. Okay. Corey also mentioned that shouldn't it be called a dual cure system? As we'll see in a minute, in dentistry or dental materials, when we talk about dual cure, we usually only refer it to as self-cure and light cure. She's technically correct that this is a dual cure because you have a self-cure and heat cure, but people usually don't refer to it that way. Okay, so now my videos are moving by themselves. What is happening? Did somebody just take over control of my, did somebody take control of my slides? Yeah. Okay. All right, so Benjamin has control of my, the heck? Benjamin Neal, would you kindly log out and log back in? Because you have control and I cannot advance my slides. There we go, I got it back. Thank you. Wow. Magic is how you did it. Okay, at least it was you and not somebody who is, who crashes into our lecture. Anyway, so that was that question. There was another question from Jimin, and the question was, do the physical stages of the acrylic processing correspond to the chemical reaction of polymerization? Yes. So there is no set molecular weight that corresponds with each stage, but basically it's as the polymerization happens and progresses, you go from the sandy to the sticky to the doughy, rubbery, and then the solid phase. Okay. All right, so let's continue. I just showed you a video of the injection molding, and this is just a brief overview of the compression molding. And as I said, I have that video up there for you to see if you want to. It's about 12 minutes, courtesy of Corey. Thank you. And anyway, so basically, you have this the acrylic in the doughy stage, okay, and you're putting it into the plaster mold, okay, so the mold cavity, and then the flask is assembled, and you apply pressure into it to squeeze out any air bubbles, okay, and then you reopen it to cut out any excess acrylic, and you put a polyethylene sheet over it, kind of as a separator, okay? And then finally, you put it back into the flask, okay? And then you can then you put it into the water bath to start curing or complete the cure. Okay? This is the fluid resin technique. It's a little bit different. Again, in this situation, you have a kind of a unique flask here, okay? And basically what they do is you have the wax and the denture teeth all made up, and then you pour in an impression material, okay? And we haven't talked about impression materials yet, and we will, but you pour in an alginate impression material and let that cure, and then you remove the cast, okay? And then you drill or not drill, but you create holes in it, so then you can pour in and then you take the plaster out, and you just saw the denture teeth remaining in there, and then you pour in the acrylic here, and this also is and in this case actually it's a self-cure system because you actually don't heat it. And then you cure it in room temperature, and then after a while you break it open, and this is just alginate, so it's easy to break open, and you get rid of the sprues, which are the holes that the acrylic was poured in through. So in this case, it's really important that an accurate reproduction of the patient's mouth and the denture is made in the alginate. Okay. Now, other than those three techniques, okay, there is also a light cure resin technique. Okay, it's not as popular, and obviously, since you have to get light to penetrate, you have to have a special mold for it. But this one is not as popular. And then they also have a microwave curing technique, and in this case, you can't use a metal flask because you have to have the microwave to be able to get through. The methyl methacrylate is asymmetrical, and that's why it can be microwave cured. And basically, it's a heat cure. You microwave it, it gets hot, and then that's how it cures. Okay? But the compression, the injection, and the fluid resin are the three main techniques. So let's talk about the heat curing process, because during the heat curing, the temperature of the cure is really important. Okay? You see, because if the temperature is too low, you're not going to get complete polymerization. You're going to get residual monomer, which then can irritate the patient as it evaporates out into, or imbibes out, dissolves out into the saliva, into the mouth. Okay. If the temperature is too high, the methyl methacrylate will boil, because its boiling point is 100 degrees Celsius. Okay, and yeah, the boiling water is 100 degrees. So why is it boiling? It's because the reaction is an exothermic reaction. So it actually builds its own heat, and you get higher than 100 degrees. So that's why it boils, and then you get porosity because of the boiling. Okay. So what we see here is, I hate this little bar that comes out. Anyway, as the water is heated up, okay, if it's heated up too quickly, you have the plaster following along, okay, and then the acrylic then follows. But because as it reacts, you have the exothermic reaction, the heat builds and it gets to almost 140 degrees Celsius. Okay? So that's why there is a monomer boil in that situation. So there are some alternate heating cycles. So this is C is when you put it in boiling water, okay, and that's no good. And B is when you heat the water up too quickly, and you still get monomer boil here. Okay, but you can heat the water up really gradually and control it so that you don't get the boil. You just get that spike here, and you continue to heat it up to boiling point and further drive the reaction to completion. But there are other preferred heating cycles. Okay? One is just leaving it in a 72 degrees Celsius water bath until you get that spike in temperature. And then you heat up the water to 100 degrees for another hour and a half or so to drive the reaction to completion. Okay? That's one of the preferred heating methods. Okay? I have a question here. Do we ever observe residual monomeric materials reacting with the oral tissues causing aforementioned, or is that irritation described just in regards to evaporation? It doesn't react with the oral tissues, it just irritates it. So it's the evaporation or the diffusion out of the material, and that just kind of is irritating the tissue. Okay. Question. So anyway, so this is a preferred heating cycle. Another one that you could do, and this is like the compression molding does this, and even with the injection molding, and they put it under pressure. So when you have 2 atmospheres of pressure, then the boiling point of MMA jumps to about 140. So in that case, you can dump it in boiling water and it can heat up and the temperature can rise to 120, 130. And yet because the boiling point of MMA is higher, it doesn't boil and you alleviate that problem. Okay, so that's another preferred heating cycle. Okay. After the heating, the cooling is also very important. Okay? You want to cool it slowly, okay? Because the thermal expansion of the plaster and the acrylic are different. Okay, so you want to kind of cool it down slowly so that you don't have too big a difference in that, due to, for accuracy concerns. And also, if you quench it, if you cool it down too quickly, you don't give the polymer enough time to relieve any stress that it has built up because you've actually pressurized it, right, as you cured it. So you want to bring it down slowly so that any kind of stress relief can happen slowly, and you don't get warping down the road. Okay, and also after that, finishing and polishing needs to be done at low speed and wet so that you don't overheat and cause warping as well, because you're still going to have residual stresses in there. Okay. So some properties of the cured resin. The polymer beads are about 500,000 to 1 million molecular weight, and the final cured resin is about 1.2 million. And obviously, the reason we do that is because we want to be able to shape the material into the correct feature, right? The amount of residual monomer, in any case, you're still going to have some. It's about 0.2 to 0.5 initially, but it evaporates, it imbibes out, diffuses out, and so it will drop to 0 pretty quickly. And if there's too much, well, I mean, any kind of residual monomer will plasticize a resin, but too much of that will cause irritation. And it also will absorb some water, about 2% at equilibrium, which is about a 0.45% linear expansion. So let's look at some of the defects and problems that we can have with this. Basically, the first one is porosity. We talked about that. In this situation, you have here a properly polymerized specimen. Basically, there's no porosity. Okay, when you have porosity, you're going to cause mechanical problems. Those bubbles in there are basically holes that when a fracture comes through, it will just go right through it. It doesn't give any resistance to the fracture. Okay? And you'll see it. So aesthetically, it's bad. Okay? B and C are when the cure temperature was too high, and so you get boiling or evaporation of residual monomer. If you have too much of that, you didn't cure it to completion, and you had a lot of monomer left over that evaporated, and you get this kind of porosity happening throughout the material. The next diagram here, this next figure here, shows you what happens when air is included during mixing. So there wasn't enough pressure built up, okay, to squeeze out the air bubbles. And those are much larger bubbles, as you can see. Or if you don't mix it enough and you get polymerization kind of uneven throughout the material, so you have more shrinkage on one side, less on the other, and that can form porosity as well. Okay? And the last one is when you are underpacking. Again, this one has to do with insufficient pressure during polymerization, and you get really large irregular voids. Okay? All right. The next defect or problem is crazing. Crazing is when you have these surface microcracks. Okay? And it happens because of when you have tensile stresses or repeated wet drying because of the expansion and the contraction, thermocycling, same thing, expansion and contraction because of temperature. And also, if it comes in contact with a solvent, you can get these microcracks. And as these microcracks proliferate and grow, and they come in contact with each other, that's when you actually start getting a fracture. Okay? And a lot of this is reduced by cross-linking. Okay? Another major problem is dimensional inaccuracy, and there are several causes of that. First one is polymerization shrinkage. So basically what happens is when you have monomer, you have this monomer here, which has its own free space, okay? Now, when you start to polymerize it, you start to attach the ends of the monomers to each other, okay? And you can see that it's now restrained. So the free space that it occupies is drastically reduced. And for monomer, if you go from a monomer straight polymerized, you get 21% shrinkage. Okay. If we use a polymer to monomer ratio of 3:1, what happens is the polymer beads, most of it actually does not react. Okay. So you really only have, a third or a quarter of the monomer reacting. Okay. And that's why the shrinkage is reduced to 7%. And it's, again, because of the monomer to polymer reduction in the free space. Another cause of dimensional inaccuracy is mold cavity expansion. And because when you squeeze it, there's pressure in there, so the mold cavity, the plastic cavity, will also expand. If you overpack it, okay, then obviously the amount that it expands is not going to be accurate. Okay. You also have thermal expansion of the dough that causes the mold cavity to expand. So depending on how much you use, if your polymer to monomer ratios are not correct, or for whatever reason the inside of the cavity is hotter than it should be, then you can cause a different amount of expansion of the mold. Okay, but the bottom line is the system that you use has already been the mold cavity expansion has already been calculated in. Okay, so they try to match the thermal expansion of the dough, the proper packing, pressure, the mold cavity expansion, the expansion of the dough itself, and they kind of match this so that after you're done, it actually shrinks to the correct size. Okay, and since there is a shrinkage, obviously you need it to expand so that it'll come back to the correct size. You also have thermal contraction of the mold and of the acrylic that has to be properly controlled, and so how you cool after the heating is important. Now, the other part is the dimensional instability. So this is over time, right? Because it's going to affect the denture fit, patient satisfaction, of course, and in your office, it might fit properly, but maybe down the road, a week or two later, then the patient comes in and says that he or she has a sore spot because of the denture, and it could be because of warping. Okay, so that could be because of the overheating due to improper polishing, cold cure resins generally are more dimensionally stable because they are slower reacting towards the end. You heat it and then you have stress buildup, right? The cold cures cure more slowly at that point than a heat cure, and because of that, it's allowed the stress is allowed to relax a little bit more. And that's why you have more dimensional stability. And the other problem is fracture. Okay? Acrylic is brittle and it's notch sensitive. So if you have a notch in there and you have any kind of impact, it can fracture. Okay? Even though it's cross-linked, it helps. Okay? Cross-linking absolutely helps the fracture toughness, but it's still brittle. And so they do have impact-resistant resins that are kind of rubbery, so that they can give a little bit when there is stress on it and come back. But generally, that's not really very popular. Okay? Now, the thing is, with the warping and the dimensional instability, a lot of times, if the denture is not fitting well, a lot of times the dentist doesn't find out until it's fractured for whatever reason. And then, they realize it had not been fitting well. Having a certain degree of fracturability has become a little bit important, and I think that's the main reason why these impact-resistant resins, these rubbery resins, are not used, because sometimes patients will go a long time with dentures that are really ill-fitting without coming for help because it's not fractured. Okay. So I have a question here. When a patient is getting adjustments on the final denture, how can we limit dentist-induced defects while adjusting the sore spots? So that question I am not able to answer because I'm not a dentist, and I would need to defer that question to your clinical professors for that. Okay? But usually if it doesn't fit, they just throw it away, and it has to be redone. So I don't know if I mentioned this to you, but I've heard from various PROS residents doing research in my lab that I see them sometimes in the labs until like really late hours because they're making dentures that really aren't perfect. And unfortunately, sore spots are easy to happen if they're not fitting well. And my understanding is that it is thrown out and remade. So I guess I don't know if they need to remake the cast, make sure that was made correctly. But a lot of times it's the labs that have to redo the dentures. Okay, any other questions? Okay, I think somebody's. Could you explain why fatigue resistance is bad? Yeah, it's not bad. So it's really more of a practical matter. But my understanding is, so are you asking fatigue resistance as far as just straight mechanical properties are concerned, or are you talking about fracture resistance here? Fracture resistance, yeah. So fracture resistance is not bad. Obviously, if you have better fracture resistance, it would be more long-lasting. It's just that one disadvantage is that a lot of patients don't come to get help or to get their dentures redone if it's ill-fitting until it's broken. And so there's been some issues with that. It's really more of a practical issue. It's not that it's bad. And I think that might be one reason why these impact-resistant resins are not as popular, because ill-fitting dentures happen, and the dentists are not getting a chance to fix that until it fractures. But if it doesn't fracture, then patients go a long time until they get their the sores and the sore spots get pretty extreme. And so that's just kind of a disadvantage of that. I hope that explained it. Okay. Any other questions? Yeah, I don't see anybody typing. So in that case, actually what I would like to do is, since we only went 30 minutes, is let's actually go ahead and do the quiz now. And then it'll give me a full, almost 2 hours to go through the composites, which is a longer lecture. Okay? So let's take the quiz now. I've already published the quiz, and if you would all log into, or whatever you do to get into the quiz, lockdown browser is required, and I will give you the password. Let's see. Oh, for some reason that disappeared. So I guess it doesn't require a password now. I don't know why. So let's go ahead and take it. Okay. Can somebody tell me if you were able to log into the quiz successfully? Yes, you can have a blank piece of paper and show on camera that it's blank. I'm not sure you need it though. I think you automatically leave this, right? Once you get into lockdown browser, and when you're done, please come back. Okay, so there is an access code needed. You know, it's weird because when I went in there to see it, it says that there's no access code. Let's see. So this is the problem, the embarrassing problem. It's that I don't remember what the code is because they usually show you. Oh, shoot. Okay, so what I'm going to do is, oh, I know, maybe I have to go to, okay, I got it, sorry. Sorry about that, everyone. Here we go, okay? This is the password. It's nylon, but it's capital N-Y, 1 instead of the L, 0 instead of the O, and small n. So you can, I think, just copy and paste it. Please begin. Oh, I thought I pasted it. My bad. Please begin. And we will start our next lecture. It's already 38, so at 10 o'clock.
Dr. Wang, the access code is not working.
Okay. Did you type, did you copy and paste? It's a capital N, Y, 1 instead of the L, 0, and N. Can you try that? It is not 1. It's L. Okay, thank you. Somebody, okay. Sorry about that. So it is capital N, Y, L, 0, N. Boy, please try that. Sorry about that. Hey, there are 14 of you who hey, I still see 6 people struggling. Sorry. Is there anyone who has not started yet? Well, there's 6. Can you let me know where you are with this? Okay, 4 people still hasn't started. We haven't started.
Can somebody who has completed the quiz let me know what's going on? Because I'm seeing some people taking multiple attempts at the quiz. That should not be possible. Okay, thanks for the feedback. I don't know what's going on. I think I'll need to get with Jason to get that, but yeah, I think we might need to. Well, I hope my voice did not bother you when you were taking the quiz. I think some people, for some reason, got started really late. So let's give them about 10 more minutes, and let's start the lecture at 10:10. So those of you who are done, go restroom or get a drink or something. There are still 3 people who are taking the quiz. So the question about why you cannot leave the browser is because the exam hasn't finished. I think there's one more person. When they are completed, then I believe you should be able to close the browser. Okay, so I believe everybody has finished. If you are still working on the quiz, let me know, but I don't think that's the case. I'm going to go ahead and okay. That was that. So we have 3 more minutes for you to take a break if you need to, and then we'll get started with the composites lecture. So are you able to close that browser? You should be able to. Okay, so it's 10:10, so let's get started again. Can somebody confirm that you can hear me? Just so that, okay, good. There was a question about, one of the questions there, somebody said that there seems to be more than one answer, and they only put one answer. That's all you need to do. If there, and you will get questions where there are more than one answer for blank. If that's the case, then you just need to type in one answer unless I ask for more than one. The only exception is usually the multiple choice with select all that apply, and I tell you that select all that apply. In that case, there will be more than one answer. Okay, so if you only put one answer in the blank, not to worry, that's all you needed to do. And that's why I didn't say anything. Okay, yeah, I guess there are other people who are concerned about that. Good, that means you know your stuff. If you put two, I go in there and mark that correct. So don't worry about if you put two. For the fill in the blanks, I do go in and double check your answers because obviously spelling errors would automatically be counted wrong. And if it's close enough, I usually give you the credit for that. So I go in and double check that. Okay, so let's get started with our next lecture, the composites lecture. This is a little long, so we'll try to get through this. Okay. Hold on. Okay, all right. So I guess locking the screen until the quiz is done and has a lot of glitches, so I will not use that next time. Okay, so let's move into our composite lecture. And it really follows very nicely from our denture acrylic lecture. So let's start off with some definitions. So a composite resin is basically a plastic material reinforced with a dispersion of glass, crystalline, or resin filler particles. Okay, and you really do need three components to this. Although, I mean, you could have a composite with just two components, but for this to really work well and give us all of the advantages of a composite, you really do need three. And that is a matrix, which is the continuous phase, and that would be the polymer resin. The filler, which usually is glass particles. It could be resin particles, but glass particles. And a coupling agent, which chemically bonds the filler particle to the matrix. So polymethyl methacrylate, what we just had, you had the powder and the liquid is not a composite because it's the same material. And after it's cured, it's just all PMMA, okay? So that wouldn't be a composite. If you had glass particles in there and you just had glass particle and the MMA, that would be a composite, although probably not a very good one, okay? And we'll talk about why that's the case. So composites in dentistry are used as restorations for cavities. They can be used as cements for bonding porcelain veneers or even metal bridges, and that's called Maryland bridges. They can be used as indirect filling materials, meaning you cure the material, make the inlay outside, and then you put it in, okay? So it can be used as composite inlays, or you could use it as a cement for bonding pre-made porcelain inserts, okay? And it can also be used, of course, the biggest use is direct filling materials, where you put the material into the prepared cavity and then you cure the material directly using a handheld light source. So just a brief history, and the reason why this is important, some people have said, well, why do we need to know the history? Is because the development of this shows you the different components and why there had to be these kinds of advancements, and gives you an overview of all of the different things that have happened that are in composite resins right now, okay? So starting off, silicates were originally used because they were aesthetic, okay? But they were not very biocompatible. They had some solubility issues, eroded easily, poor mechanical properties, crazing. The only good thing about silicates was that they release fluoride. And so they can still be used today for pediatric patients, pedo patients, and situations where caries is a big problem, but that's very rare. Okay. And then in the 50s, you had the original development of using unfilled acrylic resins, just polymethyl methacrylate. Okay. But again, poor wear resistance, very high shrinkage. 7% is unacceptable. Okay. Because it pulled away from the cavity walls, allowed a lot of gap to form, allowed secondary caries to form, leakage, staining, you name it. And then they had filled composites, okay? But they were unbonded. And because of that, they still shrank, even though they were filled. And, PMMA is kind of a filled material, I guess, because you use powder. But they had glass filler in there, but because it was unbonded to the dentin surface, when it shrank, it still created that marginal gap problem. The marginal gap is still one of the biggest reasons for failure. Staining is a reason for replacement. That's where secondary caries still happen. Okay. And then in the 1960s, Ray Bowen from the National Institutes of Standards and Technology and the ADA created a molecule called bis-GMA, and we're going to talk a little bit more about that. Okay. And it's a large molecule that's used to reduce shrinkage. On top of that, he also developed a coupling agent that bonded the glass particles to the bis-GMA and really created the first, true composite. Okay? And you can see since then there've been tremendous number of advancements. You can see here they started off with a self-cure system, and then they went to UV light, which they quickly abandoned. I hope you understand why. And now we have the visible light cured systems, mainly the quartz tungsten halide systems, which is a little bit older now, and most people use LED lights now. But the LEDs are much more expensive, okay? But have a ton of advantages over the QTH lights. There are a couple of other types of curing lights, but not as widely used, okay? And then you can see that there were advancements in the filler. So going from macrofill, which are very large filler particles, to smaller filler particles, and then to then the advancement of dentin bonding systems, which we will learn about after the exam. Okay, and you have the first dentin bonded composites, which improved its longevity tremendously. Before that, they had enamel bonding, which was easier. But you can imagine when you create a cavity, the amount of enamel that's exposed is so small compared to the dentin, the bond really wasn't very good. And then after that, they've had other types of composites and classified based on some of their properties, like flowables, which can be used for as pit and fissure sealants or as a first layer of a composite. Packables, which are supposed to be kind of more like amalgam, but not really. And then they have these hybrid systems, which we'll talk more about, but really gave rise to composites that can be used in multiple applications, a little bit more aesthetic, and yet still fairly strong. And then I talked about how shrinkage was a major problem. Low shrinkage composites were developed. That actually allowed the development of something called bulk fill composites, where you can use fewer layers, bulk fill flowables, and then now we have these universal composites, which is claimed to be usable for all types of cavity perforation. Okay, and we'll go into all of these. This is a kind of a nice overview of what's to come. So composites have really skyrocketed in popularity because of the controversy of amalgam. Obviously, it's also amalgam is not very aesthetic, not tooth colored. There's problems with disposal. I mean, it's just a hassle. And then, of course, there are some concerns about toxicity of mercury leaching out of amalgam, although there really is no scientific, strong scientific proof of that. But in Europe, amalgam is already banned, so there's no amalgam there. And the utility of amalgam really is it's much easier to place. The longevity is outstanding. It's easy to carve, and it just lasts very long. So it's still the gold standard that composites are compared with, and it's also obviously much cheaper. So it still has utility. As I said, composites are aesthetic, and over the years, because of the improved mechanical properties of highly filled composites, they're getting closer and closer to really being a viable replacement for amalgam. Okay. So the advantages of composites include aesthetic colors and shades, direct intraoral application. It actually is very good at insulating pulp from sensitivity to heat and cold. Amalgam being a metal alloy, obviously doesn't do that as well. Does not corrode or dissolve. It's adhesive to acid-etched enamel, as well as dentin with a dentin bonding agent. So this is what has made this really more usable. There's some variable advantages, and what I mean by that is it depends on the composite. A type of composite depends on the brand, whether these advantages are true. First, those with smaller filler particles are polishable. Okay? So usually anterior composites are very aesthetic, they're polishable. Posterior composites really are in general focused more on strength and fracture toughness, and those are not as polishable, and generally they're not visible, so it doesn't matter. Although I was told that dentists are increasingly using aesthetic composites in the posterior because patients who normally, when a patient gets a posterior composite, many of them go home and do this, and so a composite that they would never see is all of a sudden visible, and so then they complain about aesthetics, and that's why some dentists do that. In general, though, you don't really want to be putting an aesthetic anterior composite into the posterior area because it doesn't have the mechanical properties. Now, that's changing because of the advancements, and we'll talk about that. Those that have larger filler particles tend to be strong and more wear resistant. These composites have acceptable color stability compared to PMMA or other type of self-cure composites and things like that. So light cure has more acceptable color stability. They're resistant to water softening and dissolution. Again, that depends on the composite because more recently they've realized that we're having problems with composite degradation, and that's contributing to a shortened longevity compared to in vitro tests and research results. They can be made radio-opaque depending on the kind of heavy metal filler that's also used for that. But there are still some disadvantages. I keep talking about cure shrinkage and shrinkage stress because that's still a major problem. Incomplete curing. So because a lot of these are light cure materials, you have to stick these light cure handheld curing lights into the mouth. Now, with the LEDs, you have a much slimmer form factor, so it's really improved that. But before, with the tungsten halide, quartz tungsten halide lamps, the tip used to look like this. So you need to try to stick this all the way back into the back of the mouth, and that's really not easy. And the angle of the light really makes a big difference as to how well it cures. And so we've had a lot of problems with incomplete curing due to technique and accessibility to the posterior area of the mouth. There's still some problems with thermal expansion mismatch with the tooth because it's not the same, and it actually expands and contracts more than the tooth. We'll talk about that. Leakage, I talked about that because of the shrinkage or gap formation. There can be leakage of bacteria, acid and stuff like that into the crevice, as well as leakage of unreacted monomers and other chemicals or degradation products leaching out. So we have that problem. And that can be a place for secondary caries. Wear is an issue because you're going to chew. Some people grind their teeth. In fact, I just saw an article today saying that there's been a skyrocketing of fractured tooth. And I'm sure there'll be the same thing with fractured composites because people are being more stressed by the pandemic and grinding their teeth. Lack of radiopacity because it's not as radiopaque as amalgam. And so sometimes it's a little tricky to tell, as well as degradation, which I just talked about. So let's talk about the three main components. Okay? The first one is the matrix. And the matrix consists of, which is a continuous phase, consists of cross-linked polymer structure, okay? Which means that each of the monomers actually have more than one reactive group. So that's why the whole structure is cross-linked. It's the phase in which the filler is dispersed. And the most widely used matrix monomers are bis-GMA, which I briefly talked about. We'll talk more about that. And urethane dimethacrylate, or UDMA. So we usually tend to talk about bis-GMA-based composite and UDMA-based composites. So as I mentioned before, Ray Bowen was the one who developed bis-GMA. Basically, they tried to use epoxy, which if you do any kind of craft, you know they sell epoxy glue. It's similar to that. So they tried to use epoxy to make these composites. However, because they don't shrink very much. However, the problem is at that time, a biocompatible, hydrolytically stable initiator system was not available. And so Ray Bowen, what he did was took, at that time, BPA, bisphenol A, which was very cheap and very widely available, that epoxy, and reacted it with two methacrylate groups and created bis-GMA, okay, which is bisphenol A glycidyl dimethacrylate. And so this is a 2 there. So there are two methacrylate groups attached, one on each side of bis-GMA. Okay? And what it did was it created a much larger molecule. Yeah, I think of this as twice as long, right? Than methyl methacrylate. And because of that, there were fewer reactions, so much less shrinkage. So that's called double bond dilution, where you use a large monomer to reduce the number of reactions taking place, which then in turn will reduce the number of times the free space is reduced, and hence reduces shrinkage. I have a question here. Are we supposed to memorize the structures? No, you do not need to memorize the structures for the monomers, just the names and what they are and their function. Okay? What did you say it is called? Oh, glycidyl bisphenol A, which is this, BPA, glycidyl dimethacrylate. So this glycidyl dimethacrylate, GMA, okay? By the way, when I said BPA, I hope it rang a bell because BPA has been in the news for the last 10, 15 years because it was found that it's a xenoestrogen. It has an estrogenic effect, yes. And so it's banned from baby bottles now. So the concern, one of the concerns now, although that concern seems to have died down a little bit, is that the degradation byproduct, or one of the degradation byproducts, is something like a BPA from composites. So about 7, 8 years ago, the government tasked the NIH to develop BPA-free, yes, BPA-free composites. And so we were one of the 5 institutions in the country who got funded for that to develop a different system. So anyway, so they're still working on that. The public outrage seems to have died down, so I don't know what that means for this development. But anyway, this is basically the first system. And one of the things about this, Jimmy, is it's very, very strong. Okay? So it's not easy making a replacement for BIS-GMA. Okay. Now, a problem with BIS-GMA is because this is very long, it is very viscous. Okay, so Corey was nice enough to make videos for us to see what it looks like. And so this is BIS-GMA, okay? And you can see how viscous that is, right? So if you try to fill that with filler, and in modern day composites, we're talking 70 to 80% by volume. If you try to get all that powder in there and fill it, it's tremendously difficult, okay? So because of that, dilution monomers or diluent monomers are used, okay? And the one that's mainly used is triethylene glycol dimethacrylate, TEGMA, okay? And you can see it's a much smaller dimethacrylate, okay? So while this is also a matrix monomer, it's called a dilution monomer because it's used to adjust the viscosity, to dilute the matrix monomer, okay? And this is what it looks like. You can see how watery that is, right? And then generally a very typical formulation of BIS-GMA and TEGMA is either a 70-30 BIS-GMA TEGMA ratio or about 60-40. And this is a 70-30 BIS-GMA TEGMA. So now it flows, right? While before the BIS-GMA was really, really thick. All, you know, it's not solid, but like honey, not even the ones that you squeeze out from the bear, the little bear. I mean, we're talking like those that come in the jars where you have to scoop it out. I mean, it's very, very sticky and very, very thick. Okay, so that's what they do. They use TEGMA to make it more flowable and mixable with the filler. So that's the matrix monomers. Now, the filler is the second component. And basically, these are glass particles, mineral glass particles. And they're used to replace the monomer. Okay? The glass particles are stronger than the polymer, so they will strengthen the composite. Since they don't react, the glass particles themselves don't react, they reduce the number of reactions, and so they reduce setting shrinkage. They control the workability because I told you these are kind of sticky. When you fill it with glass particles, it becomes very pasty and less sticky. So it controls workability. It reduces thermal expansion and contraction because it has a much lower coefficient of thermal expansion compared to polymers. Some actually are zero, close to zero. And they also decrease water absorption because they can't expand. And some of them, depending on if you use heavy metal particle fillers, which usually use in small quantities, they impart radiopacity, and some can even release fluoride, depending on the material. Okay? Question here, does the presence of double bonds on both ends of TEGMA make it more desirable as a monomer? Yes, because you actually end up getting a more cross-linked situation. Okay, and we will talk more about that, so good question. So with the filler, okay, if you increase the filler loading, it increases basic material properties in general. Okay, so one of the objectives of having a dental composite is to load it with as much filler as possible. Okay. However, the limit is actually it's about 80% volume to volume. If you had filler particles exactly the same size, then it's limited to 73%, I think 73 or 74%, just because of geometry. So you have this, and if you assume they are circular too. So they're like this, stacked next to each other, you're gonna have gaps in between. And so there's a physical limit to this, okay? Now, they have other ways of increasing that, but in general, it's limited to around 80% volume to volume because of the physical limitations. If you increase the loading, you increase the viscosity. So that's one of the reasons why it's difficult to load it to the maximum. Right? And if you decrease the particle size, it increases the viscosity because it is the surface area to volume ratio increases. So there's more interaction between the filler particle and the resin, and it just further increases the viscosity. So this is a video of what a composite looks like for those of you who might not have seen one. And you can see that Corey is trying to squeeze it out. There's like a syringe, you know, a screw in the back, and he's squeezing it out. And you can see how difficult it is to squeeze out of the syringe and how pasty this is, okay? And look at the handling properties. It looks like a dough, right? So it makes it easier to manipulate because it's not sticky. Stickiness is a big problem in composites. And I've heard of clinicians who will not use a composite with superior other properties because it's too sticky. It's just a hassle. Not that you cannot use it, but it's just a hassle. Okay? So also, if you decrease particle size, however, it's more aesthetic because when you, well, let me show you. So what happens is that when you first fill the cavity with a composite and you cure it, you have a layer of polymer on top. And so it's really shiny, okay? It's shiny and smooth, but the problem is you don't end there. You actually then have to polish it. And what happens is that the polishing removes the matrix because it's softer than the glass particle. And it exposes the glass particle on the surface. So now you have, it's like cobblestone roads. That's what you have, concrete and pebbles in between, and it's very rough, okay? And depending on the size of the particle, if the size of the particle is greater than the wavelength of light, it'll start to scatter light, okay? And so it makes it look very rough, and the tongue is tremendously sensitive. So when you run your tongue over it, it will feel rough and different from your normal tube, okay? So the aesthetics is a problem when the particle size increases. So now you have two competing interests, right? You want to make a composite that is strong, and so you try to increase fill loading, and to do that, you probably have to use larger particles to make it stronger. But if the particle sizes are large, the aesthetics then has a problem. So that's why, in general, an aesthetic composite is weaker than a posterior composite, which is less aesthetic, okay? And this is a video of after you cure a composite, what it looks like. Now, there's a yellow shade because our lab has yellow light only because any kind of fluorescent light would cure the composites. But you see Corey sticking in the composite, as you can see. It's just a little Teflon flush washer. And and then she covers it with a glass just to be able to cure the surface better. And that's a LED curing lamp. You can see it's fairly slim, and it's using blue light, and she has a shield to protect her eyes. There's some UV in there as well, probably. And so she's curing for, I think, 10 seconds here, or maybe 20 seconds. Okay, and the timer stops at 20 seconds. And then, so now it's fully cured. And you can see how shiny that is, right? It's really smooth, right? And the composite, as you can see, is not transparent. It's translucent, and it's because of the particles in there, and because our teeth are not transparent, right? So it's made to look like tooth. So this filler is really important, and because of that, originally the first way of categorizing composites was based on filler, and it still is. Okay, so you have these different categories from macrofill being the largest all the way to nanofill. okay? And these are the sizes of filler particles that should be used. That doesn't mean that a manufacturer will call theirs nanofill when it may not be, and we'll talk about that a little bit more. A hybrid is when you have more than one type of filler in there, and you can see that they don't have filler that are exactly the same size. You just can't make it that way. So you have a size distribution, and the size distribution allows us to fill the material better, because if you have the same size, let's say you see these two fists, right? And you have all this gap in between. Well, if I have a smaller particle, I can fit it in between there, right? So I can increase the percent loading that way. And so naturally, there is a distribution of particle size, but then hybrids came along where they further exploited that and used larger fillers and small microfill particles, microfine particles, to do that. And then when the first low shrinkage composites came on the market, what they did was they optimized the particle size and distribution so that they could further push that and really maximize filler loading. Okay? And these are some examples of those that did that. Okay? And what that allowed them to do was improve polishability, because now you have some smaller filler particles. But depending on what the larger sizes were and how much of that was used, it determined how aesthetic they were. One other type of filler composite type was the fine particle composites. And you can see here that it's really the microfine, midi-fill, and mini-fill particles combined together. So it's a wider distribution. And it was done to increase polishability, make it a little bit better than the macrofills and the midi-fills. But these are still too large for aesthetic applications. The filler loadings were pretty good. Again, this is weight percent. The filler particles are more dense than the resin. So don't get tricked by that. Companies love to use weight percent because it's easy to measure, but it's a higher number than volume percent. So it makes their product look better. And so they had a good balance between polishability and durability. And they were kind of suitable for general anterior use, but they weren't the strongest and they weren't the prettiest. Okay? So the solution to the problem of aesthetics was obviously to use smaller particle sizes. Okay, and that's why the microfills came along. And here I say homogeneous because well, I'll talk about that a little bit later on when we talk about the heterogeneous microfills. But here, homogeneous meaning they're all glass particles. Okay, and so they used particles that were the size of 10 or 0.01 microns to 0.1 micron. So even though they're called microfill, these were really not micron-sized particles. They were much smaller than that. Okay, they're actually, if you look at this, this is 10 nanometers. This is 100 nanometers. And these are inorganic colloidal particles, and they're made by burning silane or hydrolyzing silicon tetrachloride. And they were very polishable because basically when you're down into the 10 nanometer range, and even the 100 nanometer range, that's below the wavelength of light. So it didn't scatter any light. Very, very polishable. The tongue could not tell the difference or feel it. Okay. And so this was used when aesthetics was of utmost importance because they're being so small, they were difficult to fill. So this is what what was that? This is the pyrolytic precipitation. Okay, so would you look at the PowerPoint that I sent you, because these images is not showing up. But basically here I have the silicon tetrachloride, and this is the chemical structure of silica, which is the mineral filler that it becomes. Okay, so it's basically SiO4 with 1 silicon and 4 oxygen atoms around it. and then the oxygen atom is shared with neighboring silicon atoms, okay? So anyway, that's the reaction. You don't have to know the reaction. The problem, as I was mentioning, is that when you make those microfine particles, which are really nanoparticles, okay, they aggregate it like this into long strands and aggregates. So for those of you who have been lucky enough to fix your own toilet or your sinks, what is the number one problem, most frequent problem of clogging sinks? What causes a lot of the, thank you, hair. So you would think that hair is so thin that water would just go right by it, right? Why would hair be such a big problem? Well, it's because they aggregate, they're long, and there's water tension, right? And so you just have a little bit of hair and it just clogs your sink. It's not some big rock that you put in there or pebble that you put in there, it's hair, right? And that's what was happening. Same thing here. And it was interacting with the resin and increasing the viscosity exponentially. So if we look at this graph here, we see how this is volume fraction of filler, and this is viscosity. And please note that this is a log scale, okay? And this is going from the smallest powdered quartz all the way to large glass beads. And you'll see that first, if you increase volume fraction or loading, you get an exponential increase in viscosity. But then if you reduce the size, then it further increases the viscosity exponentially, okay? And in fact, with these microparticles, the microfill, about 2% actually gives you a stiff paste. 2%, and we're talking, composites that need to be filled to 70 to 80%. Okay? So this viscosity effect is humongous, and is a major problem in composite design. So what they then came up with is heterogeneous microfilled ED composites. So you're gonna find me wince a lot when we talk about different names. It drives me crazy. The term heterogeneous is actually not used much. Instead, they call these composites microfilled. And just by the ED, you're supposed to know that it is different from microfill, which is ridiculous, okay? And I don't know how many dentists actually know that microfill composites are different from microfilled composites. Now, what are microfilled composites? That's why I like to add the word heterogeneous, because it helps me be clear, okay? Basically, they use the same inorganic colloidal particles, okay, made the same way, okay? And then what they do is they use these huge machines. They heat the monomer so that it's less viscous. They put the particles in there, and they get these huge machines to just, mix it in, okay? And then they cure it, as you see here, okay? And then they pulverize it into 5 to 50 micron size resin filler. So these filler particles are actually composites themselves, right? So they have the glass particles inside these organic filler particles, okay? And that's another word that they use, okay? Sometimes nowadays, I think another term they use is pre-polymerized particles, okay? So, or pre-polymerized filler particles. Okay? And so now they have these larger filler particles. Well, now we have larger filler particles, less effect on viscosity. You can add more of this in there and add that in with more inorganic microfine particles, okay? And by doing that, they're able to increase the filler loading to about anywhere from, I think, 40 to close to 80 weight percent, just depending on how well they do that. Yeah, obviously, the first few generations of this was much lower filler loading. Right? So now the dentist has a paste that is workable, okay? Even though you have a higher microfine particle. So it's basically, in this situation, you have an aesthetic composite which is stronger, right? Okay, so so microfill composites are basically, they have nanoparticles in there, embedded in 5 to 50 micron resin particles. I told you about this process. Some examples of this, the most famous is heliomolar, which is still used. They're highly polishable. The organic particles, although they still do scatter light, and so it actually has increased curing time. And so this is still, because it's just, the fill loading is still not up to par for posterior applications. It's still best for aesthetic applications. So these are some SEMs. This you have fine filler, which incorporates mini fill and midi fill particles. These are microfine silica for microfill homogeneous composites. And then this is the microfill composites, where you have these organic particles, much larger, with the inorganic particles embedded inside. Okay. Now, then we had a time period where nano was popular. In fact, you could buy, jeans and khaki pants with nanoparticles in it. Okay, and that was supposed to make them, iron-free, wrinkle-free kind of stuff. Okay, now they don't advertise that anymore because now we realize that nanoparticles have some biocompatibility problems. We have problems with nanoparticles inside sewage water affecting fish and things like that. So that's why you don't see that anymore. But anyway, we had the series phase, and we still do, where now they have nano-filled or nano composites. And the nanoparticle sizes are 0.1 to 100 nanometers. Okay, not that many have 0.1. And the first generation had 40 nanometer nanoparticles. So I hope you're catching this. Our microfills, the heliomolar, had 0.04 micron particles. The new nanofill composites, the first generation anyway, had 40 nanometer particles. In other words, they were the same. And it was just rebranded. Okay? However, theoretically, there is supposed to be a difference. So when we call a composite a nanofill or nanocomposite, it's not that the filler particles are smaller. Okay? Theoretically, what was supposed to have happened was that they were supposed to have fabricated it, the same pyrolytic precipitation process, but adjusted. And what it does is, as these silica particles are growing and forming, they silanate the surface. So they put a coupling agent, which we'll talk about in a bit, on the surface. And that coupling agent was supposed to prevent the nanoparticles from aggregating and forming those strands. Okay. So they're supposed to have less effect on viscosity, and theoretically it was supposed to allow you to, load up to 78 weight percent. Okay. The reality, though, is that really didn't happen, and you got smaller clusters. Okay, better than the strands, but still got smaller clusters of those particles. And though that smaller cluster was still a problem because they're not chemically bonded. And so they kind of acted like holes sometimes. and reduce the mechanical properties. Okay, so in reality, we didn't really get nanocomposites with discrete nanoparticles. Okay, it was still better than the nanofill. I mean the microfill composites. The other thing was, it turned out that not only did they have clusters, but manufacturers were actually using larger filler particles and using these nanoparticles in a hybrid system. And in fact, all nanocomposites that you see on the market are really not straight nanocomposites, but actually hybrids. Okay, and so here they would blend microfiller particles, okay, and sometimes nanoparticles, and those would be called nanohybrids if they used even smaller nanoparticles, along with larger particles. Yes, there's a question there. Please go ahead and type that or speak up.
Hi, I just wanted to ask, I realized in the handout that you discussed that that was an issue with the hybrids and that we would be able to look at the, I guess, ingredients or the label to be able to tell if there was something wrong, as in it having clusters or aggregates. So is the aggregates technically the pure form of nanoparticle that we're looking for, and anything with clusters shows that there was some type of problem or it's not completely pure?
Okay, so let me clarify. So aggregates and clusters are actually synonymous, but the difference between the microfill and the nanofills is supposed to be that the microfills, you get these long strands, okay, just like hair. So the effect on the viscosity was much greater. The clusters were kind of like, you know, clusters of nanoparticles making balls, right? And so their effect on the viscosity was much less. And in fact, a lot of times they acted like large filler particles. And so they weren't really discrete nanoparticles, but big clumps of nanoparticles. The only problem is they're not as good as larger particles because these aggregates are not chemically bonded. And so if a fracture comes through, it kind of acts like a hole. Okay? So they're not as good as large filler particles. Did that help clarify? So when we look at a composite, they're not, sometimes they tell you, very rarely will they tell you that they have clusters. 3M actually says that they have clusters, and they claim that their clusters are so tightly bound that they don't weaken mechanical properties. I don't know if they made a modification to their surface, but that's what they claim. I have not seen any other company, commercial brand that claims or admits to clusters. Now they're really more geared towards nano hybrids. So that's kind of what the story is. I hope I answered your question. If not, please go ahead and ask again. So anyway, so because they're hybrids, though, they have intermediate properties between microfilled and fine particles, or nanofilled and fine particles. Again, for general use, and they can also be used in stress-prone areas. They're still not as strong as large particle composites, but the hybrids are actually really good because they are you can load the filler loading to higher than a large particle composite because you can fit those smaller particles in between. And in those that are well designed, they indeed are very, very strong. Okay? And the loading here is 75 to 80%, but now we have ones that are in the high 80% range. So just a schematic, you have the fine particles, you have the microfine, and the microfine or nanoparticles kind of squeeze in between the fine particles and pick up the gaps that are formed by the larger particles. Let me just cover a coupling agent really quickly, and then we will take a break. So the coupling agent is basically an organosilane compound. Okay? This is the silane part. This is the organic part. The most widely used is the methacryl oxypropyl trimethoxysilane. Okay, and with this, basically you have trimethoxy, okay, groups here, 3 methoxy groups, and you have the vinyl group here. So these 3 methoxy groups react with the glass surface, the silica surface, and the carbon-carbon double bond reacts with, the vinyl group reacts with the monomer as it polymerizes, and that's how it bonds the filler particle to the matrix. Okay? So you have this here, the actual reaction, you have the silane coupling agent. That's another name for it. And the 3 methoxy groups interact with the silanols on the surface, and you get a silica type bond. And then you have the polymerizable double bond here that enters into the reaction, the polymerization reaction. Okay. Some other components in the composite include the inhibitor, just to scavenge free radicals for shelf life stability. A very popular one is butylated hydroxytoluene, which is BHT. This one is actually used as a preservative in food as well. It also has optical modifiers, pigments, shades for color matching, as well as to adjust the translucency and the opacity of the composite. Okay? So it's 11 o'clock. If it's okay with you, I'd like to take a 5-minute break because we still have a lot to cover. So let's do that. Okay. We'll come back together at 11:05. Hi everyone, sorry for the short break. It took so much time doing the quiz. This kind of left me a little bit short-timed. I hope you were able to stand up and stretch a little bit. I know it's not easy listening to the same guy for 4 hours or even 3 hours, and you know, guys can start to get dazed. Anyway, so let's continue. Just trying to see where I am as far as how far I've gotten. We're about halfway, not bad. Okay. Towards the end, some of the information at the end it's really just more description, and you can read that. So even if we don't get through everything, we'll be okay. The most important part is most of this, and then the last few slides are more just kind of describing things to you. So, okay, let's move on. If you want, go ahead, stand up, stretch a little bit because we have 1 more hour to go. Right, that's one out of 25% left. 4th set, let's go. So we have another way to categorize composites is with how they're cured. Okay, and this is very similar to what we just talked about with the acrylic resins. So you have the self-cure resins, which are two-paste. Okay, advantages is that it has very good storage stability because you have separated the accelerator from the initiator. If you mix it well, you have equal degree of cure throughout. Okay, but the caveat is that you have to really mix it well. And because it cures more slowly than a light cure, it's got much lower shrinkage stress. So I've been talking a lot about shrinkage, physical shrinkage, and volumetric shrinkage. However, the shrinkage itself, although part of it, is not the real reason for the marginal gap forming between the composite and the tooth structure, okay, as it shrinks. It's the stress that it generates as it shrinks. And when that stress is large enough, then it will create this gap. It'll pull away and break the bond. Okay? And that's why there's that gap. And so even if volumetrically something has the same shrinkage, if it generates less stress, and there are several ways that happens, it actually will not be as big a problem. But self-cure resins, because they cure more slowly, the stresses are able to be relieved as it cures better, and so it actually generates less shrinkage stress. Okay? Oh, what just happened there? Okay. Anyway, so the disadvantage of that, of course, is when you're mixing, you create a lot of porosity. You actually create, include into that mix a lot of air bubbles. Okay. The accelerator which is used, the DMPT, is an aromatic amine. It has a benzene ring in that amine, and it is a major reason why the acrylic actually yellows over time. So if you, I think they sell these crafts, or you can go to Home Depot, you can buy these acrylic things. And if you make something out of it, it'll be clear. But after a while, long time, it actually turns yellow. And it's because of that. And that's a big problem for dentistry, right? So color instability. It's also difficult to mix evenly, and so you can get unequal quick cure. Sometimes that'll generate pores because of that. And there's no command setting. In other words, when you're done manipulating and you got the right shape and whatever, you have to wait. You can't just use a light and just cure it and command it to set immediately. Okay. So with light cure resins, they are the most popular for composites. Okay. They have all these advantages. There's no mixing. Okay. And it contains an initiator system that is sensitive to blue light. And we talked about camphorquinone. This is the chemical structure of that, okay? Which is oh my goodness, you drive me crazy. I saved this as a PDF too. So please use your PowerPoint, and I will just kind of point to different parts of this. Frustrating. So in this system, you have camphorquinone, okay, and that is excited by blue light, okay, and it gets into an excited state that then transfers energy to a dimethylamine, ethylmethylamine, which is a aliphatic amine, which is the initiator in this situation. Remember, in a self-cure system, the amine is the accelerator. In the light cure system, the amine is the initiator. Okay? And what that does, the two complex together, and you have camphorquinone with two DMA-EMA molecules, okay, that are complex together. Then it dissociates and creates a free radical on the amine, okay. But the camphorquinone also has two free radicals generated. So again, camphorquinone is both a photosensitizer as well as a photoinitiator, okay? And people will use either term to describe CQ. I hope that was clear going through that blank slide. Oh my goodness. Anyway, so the advantages of light cure resins: no mixing, lower porosity, stronger, no aromatic amine accelerators, so there's better color stability. However, there's still an amine in there. Camphorquinone itself is naturally yellow, so there is a little bit of a color and some color instability, but not as severe as self-cure. You have command setting. Whenever you're ready, you just flash light on it. And if you polymerize in small increments, you can lower the shrinkage because you polymerize one layer, it shrinks on itself. You polymerize another, so you kind of compensate for that shrinkage. And it also allows for multiple shades, okay? Because you can have different colors for the different increments that you use to make it more lifelike. However, there are disadvantages. The light has to travel through to be able to cure the mask, and so there's limited cure depth, and that's why generally you have to you're taught to use 2 millimeter increments. You cure and then have another increment. So it's a little bit labor intensive because you have to cure multiple layers. Okay, and many dentists don't do that to save time because they're lazy, whatever. And that is actually a major problem, major cause of composite failure. Now, the problem is composites don't fail immediately. So, you know, after 2-3 years later on, when it does fail, nobody knows why. Okay? And for some, you know, dishonest people, they don't care. Okay? It's just more money for them to repair or replace. Okay? But anyway, you know, there's limited cure depth, and we need to be aware of that. Light curing technique or problems with that is a major reason for composite failure. Got a question here. When applying layers of composite and curing each progressively, are those junctions potentially areas which compromise structural integrity of the structure? Good question. No. The reason is because just like you have the PMMA particles with monomer, the monomers are able to penetrate, have, you know, mechanical interlocking molecularly, as well as some of the monomers, or some of the monomers that have reacted have not reacted on both sides. We'll kind of come back to this a little bit later, but you have two ends that can react. In an ideal world, both would have reacted, but in reality, many of them, only one reacts. But even if only one reacts, as long as all the chains are connected, then you're fully reacted. Okay, so you have this pendant unreacted side for some of the monomers that are in the polymer chain, and so that can react with new monomer in the next layer. Okay, I hope I was clear with that, and we'll come back to that a little bit later. Okay, but that's a great question. So it does bond. The layers do bond, and we do not have problems with the layers delaminated. Okay. Another disadvantage is it's mildly sensitive to ambient light. So that's why, like in my lab, that formulation lab, we only use yellow light so that it won't, you know, the composite won't polymerize. You have to have a special lamp, the LED or the QTH lamps, which are expensive. Like an LED lamp now is like $800 sometimes, so it's not cheap. Posterior regions are difficult to reach. Talked about that. Shade lengthens exposure time. Obviously, the darker the shade that you use, it's going to be more opaque. It's more difficult for the lamp light to penetrate and react. So you're actually supposed to cure it for a longer period of time, which I'm not sure a lot of people do. And cure is also affected by other additives in there, and you can have problems with lamps, especially with the QTH lamps. One of the problems is that the lamp degrades. So it's the quartz lamps, they degrade the halogen lamps over time, and a lot of times you may not know that. So you're actually supposed to check the lamp intensity, because if the lamp weakens, then there's not going to be enough photons to actually excite the camphoquinone, so there'll be fewer reactions happening at once. Okay? So I was just talking about that, QTH lamps versus the LEDs. The bulb intensity degradation is much greater with QTH. Okay? So the LEDs are superior in many ways. Okay? Heat generation, the LED lamps are obviously much cooler than the halide lamps, halogen lamps, and bulbs are expensive, but the LEDs last so long that the cost of bulbs are much lower overall, long-term cost. Light intensity, the LEDs are much stronger than the halide lamps. So generally, QTH lamps are about 400 per centimeter squared, I think it is, and the LEDs are like 1,000 and above. So it's much stronger than the halide lamps, halogen lamps. Okay. So this is an LED lamp. This is a halogen lamp. Some other factors affecting the cure, again, the opacity, the filler size and concentration. Okay. Because the more you have, the more difficult it is to cure, because there's a mismatch between the index of refraction of the particles and the resin, and that causes opacity. Okay, so the more filler you have, the more opaque it gets. Shade, we talked about that, and the lamp orientation. Now, there are dual cure resins, okay? And dual cure resins are when you have both a light and a self-cure component. You have initiators for both. And so you mix it and it sets up very slowly, okay? And so you use that to manipulate and you have a working time. And then when you're ready, when you're finished manipulating, carving, whatever, and then you cure with light, and it'll harden immediately. Okay? The advantage of that is that you can have more complete cure if it's mixed well. Reduce shrinkage stress because part of it is curing more slowly and allowed to relieve the stress. However, there is a problem with porosity because you're mixing, and because you have the aromatic amine in there, it's less color stable than photocure. Now, we've developed actually a very low color, very color stable dual cure system in our lab. And similar systems are currently being used for something called bulk cure composites that we will talk more about later. So advances have been made in that area. Random question. Do you know if Vitrobond would be considered to, I don't know what Vitrobond is offhand. So I'd actually have to take a look at what they claim. Sorry about that. So let's look at some of the properties of composites. Okay? One property is the degree of conversion. This is degree of monomer to polymer conversion. Okay? So how many of those carbon-carbon double bonds have reacted? So basically what you do is you use a Fourier transform infrared spectrometer, measure the absorbance of the carbon-carbon double bond peak. So before you cure, then you'll have a peak there. And then after you cure, the peak decreases because the carbon-carbon double bonds become carbon-carbon single bonds. And then you take the ratio of that, and it gives you a percent of double bonds that have converted to single bonds, or percent of monomers that have converted to polymers. So methyl methacrylate, okay, conversion is 95 to 98%. It's very fluid, very small molecule, very mobile, so it does that. Okay, that's great. So 98% of the monomers have attached, or 90% of the double bonds have attached. In other words, 90% of the monomers actually have attached to form a polymer. Okay. With bis-GMA, this is bis-GMA, you have dimethacrylate here. The conversion is only 55 to 65%. Okay. However, this is much stronger than PMMA. And the reason is because although the conversion is so long, as I said, as long as one double bond has reacted and attached to the polymer, okay, it is still it is still part of the polymer. Take a look at your slides from the PowerPoint that I uploaded. So what you have are molecules that are attached to the network, and the other pendant carbon-carbon double bond kind of freely around. So in that sense, this is 50% conversion. However, that doesn't mean that the monomer hasn't reacted. So theoretically, you could have 50% conversion and 100% reaction, right? 100% of the monomer on the polymer chain, okay? Theoretically. That's theoretical, but still. So a 55 to 65% conversion is still very good for dimethacrylates. Okay? Another property is matrix constraint. Okay? Basically, the fillers have lower coefficient of thermal expansion. So what happens is that when you heat up a composite and it wants to expand, you have the filler here, you have the matrix here, matrix hole wants to expand. Okay? But the filler particle, because the coefficient of thermal expansion is lower, and because it's bonded to the matrix, doesn't expand. And so even though the matrix wants, the composite wants to expand, the filler is holding it back. And so it reduces thermal expansion. And on the contraction side, when it tries to contract, it keeps its space, and so it stops from contracting. Okay. It also, let's see, let's put this, okay. There is a limit though. Basically, as it expands, there can be fracture in the matrix or the coupling agent or the filler particle, whichever is the weakest link. And usually it's the matrix or the coupling agent. Question, yes.
Hi, Dr. Wang. Can you hear me?
Hi. Yes.
Okay. So when you say monomer to polymer conversion, are we talking about monomer to monomer joining to form the polymer, or monomers joining with polymer to increase the chain?
Both. Right?
Okay.
Because the monomer can react with another monomer. So an activated monomer can react and attack an inactivated monomer and form the chain, or it can activate it can react with a polymer as well. As long as there's a double bond, it'll react with it. So both.
Okay. Thank you, sir.
Mm-hmm. The bottom line is that the number of double bonds will decrease, and you're looking at the ratio of that. Okay. The next property is toughness. Okay. So fillers are stronger than the matrix and the coupling agent. Okay. And so when we talk about toughness, we talk about fracture toughness. Okay. So when a fracture is propagating and comes to a filler, right? If these were bonded really well, it would have to somehow go through the filler or around the filler. Okay. If there is no bond, then it just comes to the filler and just goes right around it and goes by. That's why the coupling agent is so important. But if there is a coupling agent, now it has to break those bonds, but has to be in a different direction. So just by having to change the direction, the path becomes longer, which requires more energy, and you also have to go around the filler particle. So that change in direction and increase in surface area that it has to crack through increases the energy that is required. So this is a little schematic showing that. So there's a crack propagating this way. This is the interface, and the coupling agent is usually weaker than the filler particle. So as it approaches, a void starts to open up, just because of the geometry and the stresses. Okay? And so it has to go around the particle, and while not always perpendicular, there's an extreme change in direction. And so it literally blunts the crack from going through because of that. The amount of energy that is required is much higher to go around that, especially if it's perpendicular. Then if you think about the forces being directional and the stresses being directional, you have no y direction of force going this way, and yet now you have to have something like that, and so it blunts the crack. Another property is cure shrinkage. I keep coming back to this. This is very important. Again, it's monomer based. We talked about that. It's filler mediated. The higher the filler loading, the lower the shrinkage. In the 1950s, the monomer shrinkage was 21%. Composite shrinkage with powder or just glass filler was 7%. Then with the use of bis GMA with larger monomers, shrinkage went down to 6 to 8%. And with filler in that, it went down to 1.5 to 4.5%. And typical polymerization stress is about 20 megapascals. Okay, this graph was created in one of our labs, and basically you'll see that these are different brands, and you can see the volumetric shrinkage and heliomolar actually surprisingly being fairly low, but this is kind of what they look like. 1.5 to about 3%. And this graph shows that this is the gap that can form because of the bond strength. So if you want no gap to form, okay, basically you needed to have about 24 megapascals of bond strength to stop the shrinking composite from forming that gap. Okay, 24 megapascals. So you're probably thinking, okay, what does that mean? What's the big deal? okay? It's just that 24 megapascal is equivalent to a 3,000 pound beetle on top of a 1-inch square thick stick. That is the stress being generated by a shrinking composite, okay? That's huge, right? Now, manufacturers actually have developed bonding agents that have higher than 24 megapascal bond strength, okay? But the problem, other problems start to arise. And one was fracture in the composite, or more often in the tooth. This stress is so strong. Now the bond is even stronger, so it's not going to break there. It's breaking either the resin or the tooth, okay? Fracturing the tooth because of that. So controlling shrinkage, and more importantly, shrinkage stress, is a very, very important thing. So how do we control that? How do we combat shrinkage stress? A very easy way of doing it is just incremental buildup, okay, and cavity configuration. So what that means is that you cure in layers, 2 millimeter, and as you cure, it's gonna contract, okay? But since there's a large area that is not attached to anything, it just collapses on itself and relieves the stress. And then you just put another layer on top and compensate for that shrinkage, okay? And so by doing that, you will reduce the shrinkage stress that's built up. Cavity configuration is the ratio of bonded area to non-bonded area. So if you have a high cavity configuration, high C factor, that means that the area of the bond is much higher than the unbonded area. And in that case, it'll generate more stress. So by controlling that, by using thin layers, okay, you're increasing the area of unbonded space, okay, surface. Then you're lowering the C factor. By lowering the C factor, you're able to control the shrinkage stress buildup. Okay, so that's one way to do it. Another way to do it is by controlling how you light cure. So there's something called a gel point, which it would be nice for you to know. You don't have to know, but what it means is that as a composite cures, it goes from like a gel, soft paste, to a hard material, hard and brittle. And there's a point in the mechanical properties diagram where there's a gel point where it's really solid and the stress cannot be relieved, okay? So by slowly curing it, you're allowing stresses to relieve, giving it time to relieve before it gets to the gel point, okay? And so that's called a soft start in how you cure. So two examples are ramp curing and delayed curing. Ramp curing is you start off at low intensity and slowly ramp up the intensity so that you're allowing it the stress to relieve itself as it's cured. A delayed cure is you cure it a little bit and you wait and you manipulate to whatever you want, giving it time to relieve stress, and then you cure it at high intensity, okay? So there are different, I don't know, there are different programmed ways of doing this in some of the curing lights, but that's one way to relieve the cure shrinkage and shrinkage stress. Okay? Another way is by optimizing filler size and filler size distribution and increasing loading. Okay, so we talked about the optimal optimized filler loading method before, right? And by increasing the filler loading, you're decreasing the amount of monomer there, decreasing the number of reactions and shrinkage, volumetric shrinkage. Now, that does not necessarily always mean a lower shrinkage stress, though. Okay, it just because if you cure it too quickly, if it cures too quickly, then it gets to past the gel point quickly and does not have enough time to relieve the stress. So that's another factor that has to be taken into. But in general, the lower the shrinkage, the lower the shrinkage stress. Not always, but in general. Another way is to use novel monomer systems. And these are monomers that shrink less. Okay, so this GMA was one way of doing it, right? You increase the molecular weight, and so you reduce the number of double bonds to react. It was called double bond dilution, and so you reduce the shrinkage because of that. Well, to develop low shrinkage composites, they came up with expanding monomers. Some monomers were also very large, larger than bis GMA, but they were rigid, which allowed them to pack better and slide better and reduce the viscosity that was a problem with bis GMA. Okay? And so they were able to further dilute the number of double bonds. Some use bulky monomers that slowed down the polymerization rate and relieve stress. And others phase separated and actually produced an expansion because of that. Okay, and we're going to go through each of these. So it's important to know how these composites are made to shrink less. So when we look at low shrinkage composites, usually high filler loading, large monomers, expanding monomers, or things like that. Okay, so we have the maximizing filler loading. Visco Elite LS was the first one that did that, optimized filler loading. Highly filled to 89% weight percent, very high. 75 volume percent, which is very high. Again, the theoretical volume percent for particles of the same size is 73, 74%, right? So it's very low shrinkage, and it's a posterior composite because of the very high filler loading. This is from their website, so take it with a grain of salt. But they claim to have volumetric shrinkage of 1.5%, which, depending on who measures it, may or may not be very high or very low. But compared to the others, you can see here that the helium-molar, they measured at 2.2. When we measured helium-molar, it was 1.4. So, you kind of have to take the results relatively. Shofu's beautiful bulk restorative and the two LS systems are newer systems that are also have very high filler loading, 87 weight percent, 75 volume percent. You can see that the weight percent is lower, but the volume percent is the same. And that's because their filler is a little bit less dense. Shrinkage of 1.7%, stress of 1.6 megapascal, 1/20th of what is needed, right? The beautiful 2LS, 83 weight percent, shrinkage 0.85, shrinkage stress is a little bit higher. Here, interesting, isn't it, that the shrinkage is lower, but the stress is higher. And so a lot of this has to do with sometimes how quickly it cures. With the low shrinkage monomers, one product is caloric, and the molecular weight is 895, which is, this GMA is about 500 something, 512. So it's almost double, right? It's really high molecular weight. You can see it's a very long molecule. And with these benzene rings, it's actually very rigid. Okay? And so they reduce the viscosity with the rigidity of the monomer. Another one is Endurance Septidon. You don't have to know these brands. You just have to understand the concepts, okay? Again, very high molecular weight. In this case, they have a bulky hydrophobic central ring, which kind of slows down how molecules can interact with each other and form the composite. So it slows down the polymerization rate. It's also very hydrophobic, so it decreases water absorption and creates a little bit of phase separation. So it kind of separates the monomers a little bit, so it actually creates a little bit of an expansion as it polymerizes. 3M had a product called Filtec LS, which is not a methacrylate. It is actually an epoxy system, okay? And they developed a more biocompatible, hydrolytically stable initiator system to be able to use epoxies. And basically it's a silyarene plus an oxyarene. Oxyarene is another word for epoxy. And now they have 4 functional groups you can see here. And it's the oxyranes that react. And when they react, this ring opens up to give it some expansion to counter the contraction. And so their shrinkage stress is less than 8%, 8 megapascals, and depending on the formulation, less than 1. So here's a schematic from their brochure. So you have the oxyrane here that expands and connects to the neighboring one and reduces the shrinkage. While you have a methacrylate here, you have the free space that reduces when you connect the neighboring monomers together. Okay? So here is the shrinkage, percent shrinkage of the different composites. Okay, and I can't point it because I got this stupid bar here. But the last one here, I think, is the LS, and the shrinkage percentage is less than 1%. You can see their shrinkage stress. This one, they have 4%, 4 megapascals, and the other composites that they measure, again, this is company brochure, varies anywhere from 12 to 16 megapascals, which is still very high. Okay? Now, the major issue is still biocompatibility with the curing system. Epoxies cure, they're much more exothermic during their cure than methacrylates. Methacrylates get hot enough, but epoxies cure much more exothermically, so that's a concern. And they cure more slowly, which actually allows them to relieve the curing stress, but traditionally epoxies have been very difficult to light cure, okay? This product is actually no longer on the market. From my understanding, talking to people from their company, one, it's much more expensive. It's also sticky. A lot of clinicians I've spoken with say that it's very sticky and not easy to manipulate. So it seems that those two factors kind of spell this demise. But I am pretty sure there will be other systems that use epoxy, so it's important to understand what they did because there will be modifications of that. In fact, for the last 7 years, we've been developing an oxyrain acrylate system to combat the shortcomings of the epoxy, make use of its advantages, and make a more degradation-resistant composite. So definitely need to understand this as well. Okay. Another property is wear. Okay, obviously when you grind your teeth, when you eat, it's going to wear the composite. Okay. Now the only thing is there's no real standard test method or standards on this. Generally, composites wear 10 to 20 microns per year, which doesn't sound like a lot, but over a period of time, that gets to be quite a bit. Okay. And when we test wear, or when we categorize wear, there are two types that we usually think of. Two-body wear, which is basically direct contact of the restoration with the opposing tooth, okay? And three-body wear, where you have food in between, okay? And traditionally, it was found that composites with about 1 micron particles have the highest wear resistance. Now, the problem is there is not a lot of wear testing that is done because it takes so long to do. There's not a ton of wear data out in the literature, okay? But it's something you need to understand is actually a major component of the failure. And as it wears, sometimes those filler particles will pop out, especially with the microfills. As it was wearing down, it would pop out and create more problems, increased wear, increased fracture probability. This is an SEM of a composite. This is actually a chemically activated composite. And you can see this is the tooth structure. And after 9 years, there's been substantial wear of the composite. Okay? I'm glad that there was no failure along the margin of the composite to the tooth, but it really does happen. So composites can also be classified based on manipulation characteristics. One of them is a flowable composite, basically, how flowable it is. And the way they made it flowable is that they increased the particle size and decreased the filler amount. They decreased the viscosity. Well, you can see that that's a problem. This means it's less aesthetic. This means it's not as strong. So, however, they do have some specific uses. As I said, they can be used as pit and fissure sealants on top of pit and fissures because it flows nicely and it's kind of temporary, or it can be used as the first layer in putting a composite in, because it's flowable, it flows into the nooks and crannies really well and gives it a better bond than a very viscous composite. Said that. So I'm gonna pick up the pace a little bit because we're running out of time. So another one is a condensable composite, which is supposed to feel and act more like amalgam and carvable, which is not true. Condensable means when we talk about amalgam, you'll realize that you actually condense pack the amalgam together and have the mercury condense out. That's what's called, it's condensable. Well, they use that name for these composites as packable or condensable composites. Basically, what they did was they used larger filler particles or modified their filler particle a little bit to increase the filler loading. And so they're very strong, but they really still are not like amalgam in how they handle. And obviously with larger particles, the aesthetics is not that great. So the next type is the bulk cure or the bulk fill composite. I told you that many dentists were not following the 2 millimeter guideline, and because either they're lazy or they're trying to cut time, whatever it might be. So more recently, bulk cure or bulk fill composites came on the market, and meaning you could use at least 4 to 5 micron, at least 5 micron, 5 millimeter thick increments instead of 2, and cure in bulk. Okay? To do that, they have to have several properties. First, it has to be low shrinkage or have low shrinkage stress. Otherwise, when you have such a large bulk curing, generates so much stress that you're going to get marginal failure. Okay? The cure depth, the light has to be able to penetrate at least 4 millimeters to be able to cure the mass, right? So those are some properties that it must have, right? And this became possible because of the low shrinkage resins, okay? And currently they're sold as posterior composites and as flowables. So let's look at the low shrinkage and shrinkage stress component. As I said, very, very high filler loading, high molecular weight monomers, and now they're beginning to use dual cure monomers so that you don't have to, the light is not the only way of curing it, so that it can cure the bulk of the material. Again, the dual cure also has lower shrinkage stress, right? So the advent of low color, color stable dual cure initiator system has allowed that to happen. So I hope you're seeing how everything that we learned before is kind of coming together into these new classes and products of composites. So to get an increased cure depth of 4 millimeters, right, they played with something called, they tried to make their composites more transparent. And they do that by matching index of refraction. So you can see here, generally you have glass and the resin. And when the indices of refractions don't match, you can clearly see the glass rod. But when you match it, you see how it disappears. Okay, when you can match, the better you match the indices of refraction, the more transparent this becomes. Okay, and so the more transparent it is, the easier the light is able to travel through. There's no scatter. Okay, and also they're using low color initiators. So the initiators themselves are low color, so they are not interfering with the light traveling through as well. And I've got some examples here. Okay. And finally, using dual cure, as I mentioned before, allows you to cure throughout, even if the light is not able to penetrate as well. I have a table here just showing you some of the properties of the different bulk fill composites, shrinkage and shrinkage stress and depth of cure. And I believe this is, we're getting close, but from now on, it's just kind of more descriptions of the different types of composites. So even though we don't get to finish it, if you read the handout or even the PowerPoint, it should be fairly self-explanatory. And if you have questions, you can always ask me. We've got a couple of minutes left, and I don't want to keep you beyond the allotted time. So universal composites are the newest types of composites, and they're possible because of the nanohybrid filler technology. Okay, And by universal, we're talking about you can be used as an aesthetic composite for multiple different types of cavity preparations from class 1 to class 5. Question, do we have to memorize the depth shrink? No, you don't. It's just for your understanding. But you do have to understand the parameters, what it has to achieve. Greater than 4 millimeter depth of cure, low shrinkage and low shrinkage stress, right? And they're available as universal bulk cure as well as flowable. So really the universal part of it, a lot of it has to do with the particle size and the particle loading and the hybrid nature, okay? There will be no quiz over this material because we have an exam. So you'll have double the number of questions from today's material in the exam because there's no quiz. Let's see, highly filled, great mechanical properties and aesthetics. They also use something called a chameleon effect. So by making it more translucent than regular composites, it's able to pick up color from the surrounding tooth tissue and kind of have a chameleon effect and be able to match multiple color shades. Okay? Let's see, and then there are also self-adhesive flowables where they have you don't have to use a bonding agent. That'd be nice. And these are some of the monomers they use. 10 MDP. These you need to know. They're the different types of adhesive monomers that are sometimes used in bonding agents as well. The problem with these so far is that, yeah, initially you have great bond strength, but after a while, their bond strength decreases to almost nothing. Okay? So that's something to notice. Compomers are composites and glass ionomers, which we'll talk more about in cements, but they have aluminofluorosilicate glass, which releases fluoride. And so that's the advantage of using this. Compomers really aren't that great because they don't have good mechanical properties and they don't have sustained fluoride release, and they're not that aesthetic. So kind of we talked about Beautiful, and these are hybrid composites. They use something called Bioma, which is their own proprietary technology, but they're active, bioactive, because they release fluoride as well as some other ions. The fluoride and the strontium ions are able to help form fluoroapatite and strontium apatite, which are strong minerals to prevent secondary carriers forming. Pulp dent activa is another type of bioactive material, again, releasing fluoride and helping remineralize. Okay? And I think that is it. So we were able to get through all of this. Any questions? Let's see. Question is, do we need to know all the specific differences in properties and names of examples? You do not need to know the names of examples, but you need to know what makes a composite that classification. So if it's bioactive, what makes a composite bioactive? Okay. If it's low shrinkage, what are the things that they did to make it low shrinkage? Filler loading, large monomers, expanding monomers, rigid monomer, whatever. Those things you need to know. Hope I'm clear with that. You do not need to know brand names. Any other questions? You can also use the mic if you want. Okay, it seems like there are not any other questions. So, yes, Michael, I will remember that. I hope you have a great rest of the day. Have a great lunch. There is a question above mine. Thank you. Yeah, so there will be no quiz after this. After the exam. The exam will have double the number of questions from this lecture because we don't have a quiz. The same number of questions per hour. Any other questions? Okay, and as always, I am available through email. You can set up video conferences if you have questions. I should be able to grade your quizzes by today. Again, you have 1 week to take a look at your quiz if you wanted to. So you can set up an appointment with me directly via email, and we can set up a video conference, and I can show you those. Okay, I will be online for a little bit longer if people have questions. But thank you again for toughing out the 4 hours. That was not easy. This is, I think, the longest lecture that we have. The others I should be able to finish before that. But okay, so thank you for your attention. Have a nice lunch. Okay, there doesn't seem to be any more questions. Thank you, and have a great day. Bye-bye.